Dr. Mathews était titulaire d'une bourse postdoctorale à l'Université de Calgary et a travaillé comme chercheur postdoctoral à l'Institut Carnegie à Stanford. Ces recherches visent à mieux comprendre les interactions possibles entre les activités humaines, les écosystèmes naturels et les changements climatiques futurs et à contribuer à la base de connaissances scientifiques nécessaires pour promouvoir le développement d'une politique climatique nationale et internationale. Dr. Mathews a publié plus de 90 articles de recherche sur des sujets tels que la réponse du climat aux émissions cumulées de carbone, l'estimation des émissions admissibles pour atteindre les objectifs climatiques et l'exploration des moyens équitables de partage de quotas mondial d'émissions. Dr. Mathews est membre du College of New Scholars, Artists and Scientists de la Société royale du Canada, sert de liaison scientifique entre l'Université Concordia et Future Earth et a contribué au 4e et 5e rapport du GIEC. Alors, le titre de la présentation de Damon sera Remaining Carbon Budgets, Uncertainties and Prospects for Informing Climate Mitigation Efforts. Alors, la parole est à toi, Damon.
Merci tout le monde. Est-ce que vous voyez mon écran? Ça marche bien? OK. Donc, merci beaucoup pour l'invitation. Je suis heureux de voir tous vos noms quand même dans ce format Zoom. J'espère que ça va être pas trop long quand on peut essayer de faire ces événements en personne. Mais OK, je commence. J'avais une belle intention d'essayer de parler en français pour cette conférence. Je pense que c'est une nouvelle présentation pour moi. Je l'ai créé pour un événement hier et je pense que je dois switcher en anglais. C'est des nouveaux mots pour moi. Je pense que je vais prendre beaucoup de temps pour trouver les bons mots. Donc voilà. I will speak in English. I apologize for that. I will make an effort to curb my enthusiasm and not speak too quickly. So this is my talk. I'm going to present about a couple of research papers that we've published in the last 3 or 4 months on the topic of remaining carbon budgets. So I will introduce the concept of what is a remaining carbon budget, talk about our recent paper looking at the uncertainties and the contributions to the uncertainty in estimates of the remaining carbon budget, and then we'll end with a brief overview of some of the ways the carbon budget could inform climate policy and climate mitigation. So I'm going to start with an illustrative Google search. So I did this just the other day as a way of kind of assessing public understanding of the concept. It's actually quite an interesting activity to choose a scientific concept and see if Google, in any case, gets it right. So this is what I found. If you type in carbon budget, incidentally, you get a slightly different story if you do this in French, and I did try that out last night as well. But in English, anyways, the term carbon budget, the first link that comes up is a good source that gives a correct definition. So it says in the little text here, a carbon budget is the cumulative amount of carbon dioxide, CO2 emissions permitted over a period of time. So that's basically exactly right. If you go a little bit deeper, you get this, what are variants on the question that people ask. And so again, the first one is from the same source. It gives a little bit more information. This is a number that represents the finite limits of our planet's physical system, highlights the need to reach net zero, and this idea that if we exceed the carbon budget and keep emitting carbon dioxide, temperature will keep rising. So again, these are important concepts that are correctly reflected in this definition. There's another example at the bottom of this list that links to the carbon brief post. So again, a very good overview and a correct representation of what is a carbon budget. If you look at some of the others, it gets a little bit less precise, and so this is one from WWF, so an NGO. I mean, this concept of the carbon budget spills into many different types of organizations. So scientifically, I would take a little bit exception to the use of the language greenhouse gas emissions rather than carbon dioxide. And so I would say this definition is a little bit more precise, a little bit less precise, I should say, and spilling, stretching the definition, or perhaps not being quite correct in the definition. And then there's another one here which refers to a very different concept, or at least a variant of the concept, referring to the UK carbon budget legislation that was adopted, and so recently the UK published its 6th carbon budget report, and so this is a very specific thing that's not the same as the global carbon budget that I'm going to talk about. And then, so in this example comes up in a number of different places. More and more people are thinking about what does a carbon budget mean for individual countries or for individual institutions or companies. And so there's, it's not the same concept as the global carbon budget. Furthermore, there is a different type of global carbon budget that is very commonly mixed up with the idea of a remaining carbon budget. And so if you look at the second hit on my Google search, this is from the Global Carbon Project, which every year publishes what they call the global carbon budget. This is a different thing. This is a scientifically different concept that tracks the flow of carbon through the Earth system in response to human emissions of carbon dioxide, and looks at sort of the balance, or the budget with respect to the balance of sources and sinks of carbon in the Earth system. So, it's very, it's correct to call this a carbon budget, but is a different carbon budget from the idea of allowable emissions, or emissions that are consistent with a given climate target. So I was involved in writing this paper that we published a few months ago, and this involved a very large group of co-authors, and the first challenge was to agree on what is the correct definition of the remaining carbon budget. And so this is what we landed on. So a carbon budget in general in this usage is a quantity of total CO2 emissions that is consistent with a particular level of global warming. So this is different from what we would call here the historical global carbon budget, which is the balance of sources and sinks of carbon dioxide in the Earth system. That is a different use of the term and is not the same. So this is a carbon budget. A remaining carbon budget is how much we can still emit in the future. Given how much has already been emitted, we have an amount of future emissions that are allowed. This refers to only CO2 emissions from fossil fuels and land use change up until the point of time that CO2 emissions reach net zero, and does not apply to other greenhouse gases and aerosols. So you do need to account for the additional warming that is caused by other greenhouse gases and aerosol emissions, but the carbon budget itself refers only to a quantity of CO2. So it's a very simple concept, and there's quite a few good visualizations of this idea that are available. This is one that was produced about a year ago by Piers Forster and Yuri Rugel, kind of illustrating the approach to calculating the remaining carbon budget that was taken in the special report on 1.5 degrees that was published in 2018. So, here the idea is that we have observed a certain amount of warming up until the present day, something like in this case, a little bit less than 1 degree. This warming is caused by it's related to the amount of CO2 that has already been emitted. And then in the future, there will be additional warming that is caused by non-CO2 emissions like methane, nitrous oxide. And then you have some available space that represents future warming caused by CO2 and caused by future emissions. And so this space of allowable temperature increase is the space that defines the available emissions for the remaining carbon budget. Here's another illustration using the numbers that were produced from the IPCC report in 2018, showing a quantity of cumulative CO2 emissions associated with 3 different temperature targets. So 1.5 degrees in white, 1.75 degrees in blue, and 2 degrees in red. Here's another, this one sort of presents the idea of a carbon bubble, sort of comparing the inner circle here, the remaining carbon budget, in order to meet the, well, in this case, 2 degrees. So you can see the numbers are a little bit different. And comparing that quantity of emissions to the larger quantity of emissions that is allowed, or that is contained in current reserves of coal, oil, and natural gas. Making the case that we cannot burn all available fossil fuels if we want to respect the idea of a carbon budget. And then here's another framing the carbon budget in terms of the number of years of allowable emissions. So if you know the amount of CO2 that can be emitted in the future, and we know how much CO2 we are emitting currently every year, we can obviously calculate a number of years associated with that budget. This is an interesting visualization as well. What is shown here is the historical production of carbon dioxide and the accumulation of that cumulative amount of CO2 broken down by the major emitters. So you see the 4 major emitters, the quantity of CO2 that they have emitted over time, and the amount at the top that is left to avoid exceeding the remaining, or the total carbon budget. And then, of course, there's my personal favorite illustration of this, which again, tracks the current progress of emissions, the current progress of global warming, and relates these quantities by calculating the amount of time at the current rate of emissions that we would emit the remaining carbon budget associated with 1.5 degrees. So that is what is a carbon budget. So why does this concept work? Why is it finite? Why is there a limit on CO2 emissions? The fundamental reason for this is this idea of the transient climate response to cumulative CO2 emissions, which is a relationship between temperature change and cumulative CO2 emissions that is strikingly linear. That is to say that every additional emission of CO2 produces an equivalent increase in global temperature. And of course, as long as emissions are continuing, that will continue the increase in global temperature, which means that if we want to stabilize temperature, we need to stop emitting carbon dioxide. So this is the fundamental principle that underlies the idea of a remaining carbon budget. Of course, this is a straight line, but it's not a certain line. It's not a certain relationship. Different models give a different value of the TCRE. We can look at the range of climate models, the range of uncertainty in the data, and define an uncertainty associated with this line. There are also some processes that might cause the relationship to be nonlinear. It does seem that most of these processes tend to cancel each other out, and the net result is a very robust linear relationship over a large range of total CO2 emissions. But given this relationship, and if we know the value of the TCRE, then we can very easily calculate what is the remaining carbon budget associated with a given temperature limit, with some uncertainty range that reflects the uncertainty in the value of the TCRE. So the complication here, this relationship is very straightforward. The complication is that this really only applies to the temperature that is caused by CO2 emissions. It does not reflect the climate changes that are caused by other greenhouse gas emissions or aerosol emissions. So one way of incorporating that additional contribution to warming, because obviously if we want to limit warming, we want to limit the warming caused by all emissions of greenhouse gases, not just the warming caused by CO2. So we can define a different quantity and call it the effective TCRE, which is, again, a measure of warming, but it is a measure of the total amount of warming that occurs over time in relation to the total amount of CO2 that we produce. So it's the TCRE plus an additional warming from non-CO2 emissions. This is typically not a constant value, the effective TCRE, particularly the contribution from other greenhouse gases, and the ones in particular that have short atmospheric lifetimes, can change very quickly. And so, there's no fundamental reason to expect that the effective TCRE is a linear relationship with cumulative CO2 emissions. But if we can estimate that non-CO2 contribution, then we can kind of define our temperature limit as a particular value that reflects all anthropogenic warming, and again, use the idea of the TCRE plus the reflection of non-CO2 warming to calculate the carbon budget. And of course, you would have a larger uncertainty that reflects the additional uncertainty associated with non-CO2 effects. So here's a kind of an illustration of this using some actual data from a simple climate model. This data is produced using the MAGIC climate model, which is I guess it's called a climate model emulator. And this model has been run for about 200 different scenarios that all reach net zero CO2 emissions during this century. So these scenarios are taken from the IPCC special report on 1.5 degree scenario database. And the purple line here is the model run with only CO2 emissions. And so you can see again this very striking linear relationship between cumulative CO2 emissions and temperature increase. And then the red is the simulations that include all emissions. And so you can see there is still something like a linear relationship, but there's much larger spread. The deviation from linearity at the end of the simulations is stronger than in the case of only CO2. And so this additional spread of the red dots reflects the effect of different scenarios of non-CO2 emissions, so different approaches to mitigating methane emissions to aerosol emissions, and that additional uncertainty causes this larger spread in future warming. But so if we want to know 1.5 degrees, we can kind of find the center point of this cloud of dots, estimate the remaining carbon budget, and then also quantify the spread. And so this would be the total budget. This is the amount that we have already emitted up to the present day. And then this is the available future emissions, or the remaining carbon budget. And then the uncertainty reflects this spread across, in this particular model, the spread across the cloud of scenarios that reflects the uncertainty, particularly associated with non-CO2 contributions. So obviously this particular uncertainty range is only a subset of the full uncertainty, but it illustrates the idea. So in this paper, we provided a kind of a more schematic version of this. This is effectively showing the same thing in a more idealized way. We have this TCRE relationship here. So we can quantify the warming that is caused by CO2 at a given level of total CO2 emissions. And then we need to estimate an additional warming that is likely to be caused by non-CO2 emissions in the future. And then this, point here then determines what is the carbon budget associated with level of warming. So I will talk a little bit about the numbers that were produced by the IPCC special report, which at the time were the best estimate available of the remaining carbon budget. And so these red bars down here are based on the numbers from that IPCC report. They gave various different percentiles of their distribution of the remaining carbon budget. And these were the numbers that were produced. And so the central estimate was this one, 580 billion tons of CO2 starting in 2018. And then in order to have a higher confidence of not exceeding the target, they gave a lower carbon budget, reflecting a 67% confidence of not exceeding 1.5 degrees, which is 420 billion tons of CO2. And these numbers have been widely reported by many different different, both scientists and also non-scientists, and used to emphasize the case for achieving net zero emissions. But the important thing here that most people don't actually appreciate is that this range of values that were given did not include most of the uncertain processes that affect the carbon budget. They included the uncertainty caused by the TCRE only, and they did not include many other sources of uncertainty. So if you look at the table that was produced, and so this is from chapter 2 of the IPCC report, and this is a very widely cited table. These are the numbers that I just presented. So 580 billion tons of CO2 from 2018 onward was the central estimate. But then if you look over on the right-hand side, there's 6 other sources of uncertainty that were quantified separately from the effect of the TCRE, or the uncertainty of the TCRE. So for example, we have this thing called Earth system feedbacks. And so this is things like permafrost feedbacks that may not be accounted for by this estimate of the TCRE. There's non-CO2 scenario variation. There's non-CO2 forcing. There's several other historical temperature uncertainty is another important source of uncertainty. So these were all quantified, but not actually incorporated into the central estimate of the budget itself. And so over here you have uncertainty caused by the TCRE, giving a range of plus or minus something like 200 billion tons of CO2. Over here, you have an additional uncertainty that is about 5 times larger when you add up all of the different components, plus or minus about 1,000 billion tons of CO2. And so this uncertainty, it's very important and very necessary to actually factor into the estimate of the budget itself. To illustrate this visually, again, the red bars here represent the remaining carbon budget, including only TCRE uncertainty. And if you take all these other sources of uncertainty and represent them visually, you get reasonably sized bars that contribute additional uncertainty. Some of these are what we would call geophysical uncertainty. So these are things that affect how the climate system is responding to greenhouse gas emissions in general. It could be CO2 emissions, it could be non-CO2 emissions, it could be aerosol emissions. So there's uncertainty at various levels, and many of these uncertainties affect the carbon budget itself. Some of them are not climate system uncertainties, rather are socioeconomic uncertainties. And so this is a type of uncertainty that relates to human decisions or technological processes that will determine what future emission scenarios occur. So it's not the climate response to the emissions, it's the human processes that lead to those emissions in the first place. And so we could call this scenario uncertainty, or at least scenario uncertainty is one version of socioeconomic uncertainty. Another type of uncertainty in the carbon budget estimates is just the method that is chosen. And in the IPCC report, this came up quite clearly in the choice of the representation of historical temperature increase. And so at the time, it had become clear that observational temperature data sets gave an estimate of global temperature increase that was based on spatial coverage of observations. It was based on the use of ocean water temperature combined with air temperature over land. And so, the argument was made that, depending on if you use this to define global temperature, you get a different value than if you use globally uniform measurements of surface air temperature. And so this is depending on which version of global temperature you use, you get a different estimate of the remaining carbon budget. This is not a scientific uncertainty. It's not a socioeconomic uncertainty. It's a choice that is made by the researchers. So it's a different category of uncertainty as well. So just to kind of recap these sources of uncertainty, so we have geophysical uncertainty. Anything that affects the value of the TCRE is a scientific geophysical uncertainty. There's additional uncertainty associated with non-CO2 forcings. There are potentially additional feedbacks that we don't know about or don't understand very well that contribute additional uncertainty. And then there's this idea that not all of the warming associated with past emissions has necessarily happened yet. There is the possibility of additional warming that has not yet occurred. And that additional warming is also not captured by the value of the TCRE itself. And then there's socioeconomic uncertainty, any processes basically that affect the production of emissions and how quickly those emissions occur over the future, particularly relevant to short-lived climate forces like methane and aerosols. And then we have methodological uncertainty, which could be the choice of metrics, such as how you represent global temperature. It could be the choice of baselines, for example, what is pre-industrial? What period of time do we use to represent pre-industrial? If we use an earlier period of time, obviously there is more warming that has already occurred. And so this is again, it's not a scientific uncertainty, it's a choice that researchers have to make. And then researchers could also make choices about what processes to include or exclude in the uncertainty analysis. So if you either consciously or unconsciously exclude important uncertain processes, that will also affect the estimate of the carbon budget. So the next paper I want to tell you about is, an effort to reflect all of these sources of uncertainty in the distribution estimate of the remaining carbon budget. So this is a paper that was published in January of this year in the journal Communications, Earth and Environment, and we developed a framework, kind of a fairly simple set of equations to calculate the remaining carbon budget as a function of uncertain parameters and their distributions. And so I will go through the framework fairly quickly, but there were 5 input parameters that we used. So one was an estimate of observed warming up to date. The second was an estimate of cumulative CO2 emissions up to the present day. And then there were 2 parameters representing present and future non-CO2 forcing. And then a final parameter representing this idea of unrealized future warming, or what is called here the zero emissions commitment. So this is if we were to stop emitting CO2, would temperatures continue to increase? Would they decrease? Would they remain stable at current levels? So we produced these into our simple equations and then calculated distributions of both the TCRE and the remaining carbon budget. And so all of these sources of uncertainty that in the IPCC report were quantified separately are now in this framework internalized into the calculation of the distribution of the remaining carbon budget. So just quickly to introduce the framework to you, so this is a definition of the TCRE. It's the temperature change caused by CO2 emissions divided by the total cumulative emissions over time. So you would have a number like 0.5 degrees of warming per 1,000 billion tons of CO2 emissions or something like that. So for this framework, I began by rewriting this equation like this. And so instead of temperature change caused by CO2, this is now temperature change caused by all greenhouse gas emissions. And so this is what we can observe in the historical record. This is still the total historical emissions of CO2. And then this parameter here reflects the non-CO2 contribution to warming. So FNC is the forcing fraction caused by non-CO2 emissions. And so this is the same as this equation, but just written in a way that can reflect the observations we have available. So, we can observe historical temperature increases and estimate the contribution of anthropogenic forcing to those increases, and we get a distribution that looks like this with a central estimate. You probably can't see the numbers of about 1.15 degrees of warming up to the present day. We have an estimate of the historical cumulative CO2 emissions, and the central estimate here is, well, the units are different, so don't worry about the numbers, but we have an estimate and a distribution of that value, and then we have an estimate of the current fraction of forcing that is caused by non-CO2 emissions. And the central estimate here is about 0.15. So about 15% of observed anthropogenic forcing is from everything other than CO2. Consequently, we can say that 85% of observed temperature increases are caused by CO2 by themselves. So we then estimate the TCRE, and this is our estimate of the TCRE shown in the blue line compared to the previous assessment of the TCRE in gray that was produced by the 5th assessment report of the IPCC. So we have a similar central value, but a much narrower distribution, particularly on the lower end. So our central estimate was 0.44 degrees per 1,000 billion tons of CO2 with a 5 to 95% range as shown here. And I won't go into too many details about this, but one value of this framework is it's very easy to assess the contribution of individual parameters to this uncertainty range. So that's what's shown here. The color represent the 3 different parameters that we used, and I'll only just say quickly that in the historical record, the most uncertain contribution is that of non-CO2 forcing, and this relates very strongly to aerosol forcing in particular, which is a very large uncertainty that affects many things, including the estimate of the TCRE, and as we'll see in a minute, of the remaining carbon budget itself. So if you look at our distribution then in comparison to a number of other estimates of the TCRE that have been made over time, including, oh no, there isn't one by Mathews, but many previous estimates of the TCRE using various different approaches. So our estimate at the top is very similar in some ways, but again, better constrained and a narrower range than most previous estimates of the TCRE. Okay, so now we want to take this and extend this to the remaining carbon budget itself. And so the remaining carbon budget does depend very strongly on the TCRE. So we retain these 3 parameters that were used to estimate the TCRE and add 2 more. So one is the unrealized warming from past CO2 emissions. And so the TCRE, because it represents the transient warming, much like the TCR or the transient climate response, it does not reflect what happens after emissions stop. And so we need an additional parameter to represent the potential either additional warming or cooling that occurs when we stop emitting CO2. And then the final parameter is, we can observe the current forcing caused by non-CO2 emissions, but we don't expect that fraction to stay constant over time, particularly in mitigation scenarios where CO2 emissions decrease quite quickly. We would expect the emissions of other greenhouse gases and aerosols to also change quite dramatically in those scenarios. And so we need a different estimate of the future non-CO2 contribution to warming. Okay, so taking, basically, again, simple relationships between these things, we derived this equation, and I won't go through the details of how we came to it, but this was the final estimate of the remaining carbon budget. And I'm just going to, orient you to the 3 components of the equation. The first is the estimate of total historical emissions. So this is the same parameter that was used to estimate the TCRE. The second term or collection of terms all relate to temperature itself. So the first here is the temperature limit of interest. So this would, in this analysis, I'm going to show you 1.5 degrees. This second term is the amount of committed warming from CO2 emissions. And so this needs to be taken off the temperature limit in order to allow that committed warming to occur. And then we have an estimate of the warming that has already occurred. And so collectively, these terms tell us how much available future warming there is to be caused by future CO2 emissions. And then the third term is the role of non-CO2 emissions. And so there's 2 terms here. One is the observed historical non-CO2 forcing fraction. The second is the future estimated non-CO2 forcing fraction. If the non-CO2 forcing fraction increases in the future relative to today, that means the remaining carbon budget would have to be smaller. And so that changing fraction of non-CO2 forcings is an important determinant of the remaining carbon budget. So I'm going to talk just a little bit about this future forcing because, this was a fairly technical part of the paper, and I won't dwell too much on the details, but we just have to come up with a way of estimating the future estimated non-CO2 forcing fraction, and The way we did this was to access, again, the special report on 1.5 degree scenario database, and to assess all of the scenarios where CO2 emissions reached net zero at some point during the 21st century, and then to estimate or to take the non-CO2 forcing fraction from those scenarios. The problem is, I mean, you can see here a relationship between current non-CO2 forcing and future non-CO2 forcing. There's a big spread in future non-CO2 forcing, and some of that is because of current uncertainty in forcing, and some of it is because of future scenarios of emissions. And so we did want to separate the forcing uncertainty, which is a geophysical uncertainty, from the scenario uncertainty, which is a socioeconomic uncertainty. And so I would invite you to look at the paper to kind of convince yourself that we did this correctly. But effectively what we did was to define put a regression line through these points, and to define the future forcing as a function of the current forcing in each scenario, as a reflection of the geophysical forcing uncertainty in the future. So I'm going to show you first a set of results that includes only the geophysical forcings, or the geophysical uncertainties, and none of the scenario or socioeconomic uncertainty. So this was our result. I'm using this framework, the distribution of the remaining carbon budget for 1.5 degrees. We had a median value of 440 billion tons of CO2 from 2020 onwards, and a 67, so this would be the 33rd percentile of this distribution, which gives you a 67% chance of not exceeding the 1.5 degree target. So this value was 230 billion tons of CO2. Again, we can use this framework to assess the contribution of each parameter. I won't go into the details of this, but I'm happy to answer questions if people are interested in. Finally, we did want to include the additional effect of scenario uncertainty as a different source of uncertainty. And the way we did this was to represent the vertical spread of this cloud of points and adjust the slope of this line to change the value of the future forcing in a way that would reflect socioeconomic scenario uncertainty. And when we did this, we basically did the same calculation, but the entire distribution of the remaining carbon budget shifts as a function of future scenarios of emissions. So we have the main case here, which I showed previously. If we are able to follow a scenario in the future where non-CO2 forcing decreases relative to where it is today, this would be a case where we are very successful, for example, in decreasing methane emissions from agriculture. That would allow more warming for CO2, and consequently the remaining carbon budget would be higher. If, on the other hand, we follow a scenario where the non-CO2 forcing increases, and this could be because we are unsuccessful in mitigating methane, or maybe because we are so successful in mitigating CO2 that the aerosols that are produced from coal, for example, are also removed, and that aerosol forcing, which is negative, is removed, and that process, for example, would increase the total contribution of non-CO2 forcing and decrease the carbon budget. So across the available scenarios, then, these decisions about what scenario we follow can shift the carbon budget by about plus or minus 170 billion tons of CO2. So just to summarize these numbers before I talk quickly about some of the policy implications, we produced a best estimate of 440 billion tons from 2020 onwards. The total reflection of geophysical uncertainty, including all of these uncertain factors, led to 33 to 67% range of 230 to 670 billion tons of CO2. It's worth noting that if we look at the larger 5 to 95% range, the distribution extends into negative values. And so according to our analysis, there's a 17% chance that the remaining carbon budget for 1.5 degrees is less than 0, which of course would mean that we have already emitted all of the CO2 that is required to cause temperature change to increase above 1.5 degrees. So it's not the most likely scenario, but it's a reasonably large possibility. And then we have additional socioeconomic uncertainty. Again, the reason this is separated is because this is something that reflects human choices. And so it's not necessarily something that can be quantified probabilistically, although I acknowledge that the next presentation today will discuss perhaps some ways of thinking about that. But for the moment, we have treated this as a discrete choice that can shift the distribution rather than as a formal probability. Finally, there is this issue of methodological uncertainty that, and so, fundamentally, we haven't addressed that in this paper other than to clearly state all of the choices that we made in, choosing the parameters, assessing their uncertainty, and incorporating them into the framework. And obviously, this framework can also easily accommodate new understanding and new information about those uncertain parameters and uncertain contributions to the remaining carbon budget. So finally, I want to discuss a little bit what this means in terms of climate policy. The single most important policy implication of our carbon budget is that we need to achieve net zero CO2 emissions, and we need to do that, very, very quickly. And I mean, I do think this idea is catching on. So this is a report from October of last year showing that something like 2,000 cities, regions, and companies around the world have adopted net zero targets. And so this is a reflection of the idea that we have a finite amount of CO2 we are allowed to emit, and we need to, at some point, eliminate those emissions to the atmosphere. But there's still this question of, if you are a country or a company, how do you determine what is a reasonable amount of emissions? And increasingly, people are talking about national carbon budgets. And so, how do we go from a global quantity of emissions to a national budget that's relevant to national policy? This is not a straightforward process. You need to make two very big assumptions. One is, how do you take this total quantity of emissions and allocate it over time? And secondly, how do you allocate it among countries or among potentially provinces or companies within countries? So I'm going to talk about each of these quickly. First, the question of allocating over time is the easier challenge. This is a schematic from our paper that shows, the simplest way of doing this is just to start at present day CO2 emissions and draw a straight line down to zero at some date, such that the total area under this line represents the allowable remaining carbon budget. And so in the case of 1.5 degrees, our central budget estimate would require a global net zero date of 2040. In the case of well below 2 degrees, which is something like 1.75 degrees of global warming, we could have a net zero date of 2060. And so you could take this total quantity and then just divide it into 5-year increments, and such that you would have a available global budget for a particular 5-year period, which would be consistent with the overall trajectory of emissions. And so this is exactly what the UK has done in their implementation of the carbon budget. The UK Committee on Climate Change is populated by some scientists that have quite a lot of expertise in this area. And so I would say this is a very good example of how to implement a carbon budget nationally. They have their projected emissions leading to net zero the year 2050, and have identified 5-year periods along that trajectory and calculated an allowable budget for each of those 5-year periods that decreases over time. The more difficult question is, how do you actually decide, for example, in the case of the UK, what is the reasonable carbon budget that should be allocated to the UK? Or another way of asking that question is, by what year should the UK be targeting net zero CO2 emissions? And this is a question that, that lands squarely in these principles of fairness and equity. We have a global remaining budget. We want to divide that into national allocations. There needs to be a decision on the part of who is doing the division as to how responsible individual countries are, how capable they are to decrease their emissions, and what is ultimately an equal or equitable distribution of those emissions. So this is a very difficult thing, and it's very unlikely to be successful if left to the jurisdiction of particular countries, and so there also needs to be some evaluation for consistency with the global budget. But fundamentally, the idea is that if we have a global year at which CO2 emissions need to reach net zero, if you are a rich, wealthy country that has a long history of very high CO2 emissions, your fair responsibility is to be more ambitious than the rest of the world and to target an earlier net zero year. Whereas if you are a less responsible and less wealthy country, it would be fair to allow more time for that decarbonization process. So countries like the UK and Canada should clearly be on the earlier end. And so you could suggest that the UK's net zero target by 2050 is perhaps fair and ambitious with respect to a well below 2-degree target. It is not consistent with a 1.5-degree target. If we want to actually achieve 1.5 degrees, richer countries should be targeting net zero emissions before 2040. So just in the last couple of minutes, very quickly, the last year has obviously changed a lot of things in the world, and one of the things that it has changed is the production of CO2 emissions. And so, for the first time ever in the history of CO2 emissions, global emissions in 2020 dropped by about 7% relative to 2019. And I mean, this is kind of a big deal. It was not done on purpose. This was a side effect of COVID lockdowns. But there are nevertheless lessons to be learned. And one of the lessons or insights is that if we look at the range of emission scenarios that would take us to 1.5 degrees, the amount that emissions decreased in 2020 is very consistent with those scenarios. And so the challenge going forward is to how to maintain that decrease. Obviously, the intent of COVID lockdowns was not to decrease emissions, but a lot of money has been spent on supporting those lockdowns. And if even a fraction of that money was actually spent on intentionally trying to decrease CO2 emissions, a lot of progress could be made. And this is one interesting paper that I encountered a few months ago that looked at the total amount that is currently being spent in government stimulus packages surrounding COVID-19 and compared that to estimates of how much money is needed in order to shift energy production to renewable sources and to decarbonize along emissions pathways that are compatible with Paris. And the total amount being spent right now is much, much larger than what would be needed to actually solve the climate problem. And so there's certainly potential for green recovery stimulus spending to accelerate the decreases in CO2 that we've already seen and kind of encourage the pathway towards net zero emissions. This is another example that I encountered just a couple of days ago. This is an analysis of how green are various countries' stimulus package, and I don't know much about the source of this other than to put it up as an illustration of efforts to kind of ask this question of whether COVID stimulus spending is being helpful in terms of climate or not. But this is basically the challenge at this point. This is from the Climate Action Tracker website, which is one of my preferred sources of information for national climate policy. So they've shown global emissions that decreased in 2020, and as of September last year when this report was produced, their estimate of kind of the policies that are in place would lead to emissions rebounding and continuing to increase along historical trajectories. And so the really important question right now is can the green stimulus money be used to close this emissions gap? And really that will determine the lasting effect of COVID with respect to climate action. So to conclude, remaining carbon budgets are, a very appealing way to frame the climate challenge. They are quite simple, easy to understand, although surprisingly easy to misinterpret. It does represent a finite cap on allowable emissions, requires net zero targets both globally and nationally. But when talking about national targets and even subnational targets, we also need to consider fairness principles. The geophysical basis of the carbon budget is the TCRE. So any uncertainty that affects the TCRE also affects the carbon budget. And then there's, of course, additional geophysical uncertainty that is not included by the TCRE that needs to be included. There is also socioeconomic uncertainty that is different because it reflects human choices about what we emit in the future. And so our framework that we developed to kind of incorporate these uncertainties produced a new estimate. And this estimate is about equivalent to 11 years of current emissions before we emit the remaining carbon budget for 1.5 degrees. And so, this idea of green recovery from COVID is very important and will ultimately decide or determine whether or not we are able to embark on a course for net zero emissions or whether the Paris targets will be ultimately out of reach. So thank you. I'm happy to take questions.
Merci beaucoup, Damon, pour cette présentation très intéressante. Donc, je ne sais pas s'il y a des questions, simplement inscrire votre nom dans le chat. On vous donnera ensuite la parole. Je peux... excusez, le facteur. Je peux peut-être commencer avec une question. Bon, il y en avait une, mais je vais y aller avec ma question. Tu avais présenté le 5 to 95% range of the carbon budget. Could you explain a bit what is how to interpret these negative values that we get in the range? Does it mean that the unrealized warming is already too large, so it already reached the 1.5 degrees? And so if it is like this, there's no purpose to remove more CO2 as the unrealized warming already reached the 1.5. So maybe I interpret incorrectly the numbers.
Yeah. So in order to be on that end of the distribution, we would the estimate of the unrealized warming from CO2 emissions. There was a recent paper that estimated the range across different climate models. If we were to stop emitting CO2, at some point in an increasing CO2 scenario, and for the level of emissions associated with 1.5 degrees, the range was plus or minus 0.3 degrees across the simulations. And so if you're at the high end of that range and there's already 0.3 degrees of warming just from past emissions, then yeah, you're going to cross 1.5 degrees. The other thing that could cause that is if the current aerosol forcing is very, very strong, that means that the TCRE is actually very high, and so that would be the other way that could be the case is if the warming from CO2 is actually much stronger than we think because it's being masked by very strong aerosol forcing. And if that's the case, then as soon as you remove that aerosol forcing, temperatures will rebound and cross 1.5 degrees. So those are the kind of the two scenarios where we could have a negative remaining carbon budget if one of those two extremes is the case.
Okay, thank you. Donc, il y a quelques questions. Frédéric Julien?
Oui, je voulais savoir, en ce qui concerne les cibles d'émissions nettes nulles au niveau national, donc on comprend là, que selon la capacité des pays, etc., la date devrait changer. Peut-être que le Royaume-Uni, par exemple, devrait aller vers 2040 ou 2030, enfin, plutôt que 2050. Mais je remarque que les cibles d'émissions net nulles, en général, sont exprimées pour l'ensemble des gaz à effet de serre, donc mesurés en équivalent CO2. Or, donc, comme vous l'avez bien expliqué, les budgets carbone sont plutôt mesurés en CO2 simplement. Est-ce que ça signifie que les pays devraient se donner des cibles d'émissions net nulles de CO2 plus précisément pour éviter, par exemple, je ne sais pas, qu'on réduise davantage le méthane ou d'autres gaz, des gaz à plus courte durée de vie là, que le CO2?
Yeah, I mean, that's an excellent question, and yes, effectively, it would be much stronger alignment with the idea of a carbon budget for countries to propose net zero targets for CO2 only. And part of the reason for doing that is that if you have a net zero target for all greenhouse gases, then the effect of that target is dependent on what metric you use to calculate the CO2 equivalency of other greenhouse gases. And so if you use global warming 100, you're going to have a different climate outcome than if you use global warming 50, global warming potential, or global temperature potential. I mean, there's a variety of different metrics, and some of them are more accurate than others. And so a net zero all greenhouse gas emissions is a less precise target that depends on metric choices. If you look at the UK's carbon budget report, their net zero 2050 target actually does, so they do articulate an earlier net zero target for CO2 only. So again, that is actually a good representation of how countries should proceed. I believe their CO2 only scenario reaches net zero around 2045. So it's a little bit earlier than the net zero target for all emissions.
Il y a Jean-Marie qui a une question.
Oui, ma question c'est, est-ce qu'on réussit à publier ce genre de trucs dans les journaux? Par exemple, le 11 ans, est-ce que vous vous attendez à ce que certains journaux le publient?
I mean, so this 11 years, there's a number of places where that number has been published. I mean, it was in the special report on 1.5 degrees, but it was not, strictly speaking, related to the carbon budget. Most papers that include an estimate of the carbon budget will kind of translate that into emissions years. So it's quite common for that to be the case. I mean, the confusion is that, if emissions stay at current levels, then we will emit the remaining carbon budget in 11 years. But of course, if emissions start to decrease and follow a trajectory to net zero, then we have 22 years in order to get there. So it is a bit, it can be a confusing translation of the data to talk about emissions years, because it depends on what the emissions actually do.
Une autre question de Thomas Dandres.
Oui, bonjour. Merci beaucoup pour la présentation. C'était très clair, très intéressant. Je vais poser ma question en anglais. So, I can imagine that the rate of carbon emission has decreased due to COVID-19. But when I look at the CO2 concentration in the atmosphere, it is still rising. And I don't know how to conciliate that with the reduction in CO2 emissions. Because I thought that when you emit CO2, it would take only a few months before it affects the concentration in the atmosphere.
So, I mean, the reason that concentrations are still rising is because global carbon sinks, so the oceans and the forests of the world absorb about 45% of the CO2 that we emit, and so 55% of the CO2 we emit will stay in the atmosphere. So if we decrease total emissions by 7%, we still have 50% of, so there's still a large quantity, much higher emissions than carbon sinks are able to absorb. So if we were to cut emissions by 50%, we would see CO2 levels in the atmosphere start to stabilize. But then the carbon sinks would also respond to that change in emissions and would weaken. So really, if we want to stabilize CO2 levels in the atmosphere, we need to cut emissions by 60 or 70% and then continue to decrease them over time in order to maintain that stabilization. So it's basically that the decrease, even 7% is a large decrease, but it's too small to be seen in the atmosphere. I mean, I think, okay, I would say that, we should actually see a, maybe 2 or 3% decrease in the rate of increase in the atmosphere this year, something like that. But it's still going to increase. So instead of increasing by 3% this year, maybe it will increase by 2.8%, because that's about the amount by which emissions decrease.
Okay, thank you. Great explanation.
Merci. Il y a quand même d'autres questions dans le chat. Là, on a dépassé notre temps, donc on va devoir passer à la prochaine présentation.